In part 3, we'll be totally switching gears to something totally new. We're going to talk a little bit about what are called isomers. Now, there are two major classes of isomers. The first are called constitutional isomers. And as you can see, they differ in the arrangement of atoms. That means that they have the same molecular formula, but they have a different structural formula. So an example would be this compound and this compound. Their molecular formulas are exactly the same. They have the same number of carbons, they have the same number of hydrogens, but they differ in where those atoms are arranged together in space. Stereoisomers, on the other hand, differ in the spatial arrangement of atoms, and that means that they have a different look in 3 dimensions. Now, these drawings here are clearly only in 2 dimensions. I can't draw anything 3-dimensional on a 2-dimensional board. So what we do on 2-dimensional paper to show that we have stereoisomers are what are called this notation where you have a wedge and a dash. Now, this is not something that I need you to be really proficient at. And I'm not going to ask you to draw any stereoisomers on wedges or dashes. But just to know what the notation looks like, this means that this chlorine atom is coming out of the board. So if you were to look at this molecule in space, you would see that the chlorine molecule is coming here out of the board. And here in this case, this chlorine molecule is actually going out of the board. So if this was the plane, if my hand was the plane of the board, it would look like this, where the chlorine would be coming, going out in the back. So on the wedge, it's coming forward. On the dash, it's going behind. Okay, what does this mean? Well, actually, these 2 compounds are written like this in 2 dimensions. And in 3 dimensions, they're differentiated as to where that chlorine is. Is it in the front or is it in the back? Okay. So let's talk a little bit about those stereoisomers. And let's compare what are called chiral and achiral molecules. A chiral molecule has a mirror image that is not superimposed. In other words, if you took a molecule, let's say that my right hand is a molecule, and I were to take its mirror image, my left hand is its exact mirror image, and I were to try to put them so that they were superimposed, which means that I would try to lay my hands in such a way that they would be exactly the same together, you can't do it. There's no way to superimpose your left hand on your right hand. You can try to go like this, but you're not looking at the same side of the molecule. You're looking at the palm of my right hand and the back of my left hand. So hands are an example, are a good description of 2 mirror images that are not superimposable. If you're a molecule that's like a right and the left hand, you're what we call chiral. They're not superimposable. Here, achiral images have, achiral molecules have mirror images that are superimposable. And if I were to take this marker and take its mirror image, it would look exactly like this. And what I could do is just spin the marker around so that I could put them exactly on top of each other and they would be interchangeable. think of something else that I have in the classroom that would be a mirror image, so it would be a little easier to see. Here I have a black marker and a red marker. Let's just pretend that they're the same color. So if I were to take my black marker and to take its exact mirror image, I would put them end to end. Now try to superimpose them. Well, that's not superimposed, but if I stack it like this, all I have to do is flip it around and it fits. Now let's try to do that with our hands again. So I was just able to flip my marker around and it fit. If I flip my hand around, remember, I'm looking at two different sides of my molecule, so it's not superimposable. So this is, the example is your left and right hands. An example of a chiral molecule, anything that's symmetrical, are all symmetrical molecules are achiral. For example, H2O. This is my mirror. That's the mirror image. Well, that mirror image, if you take this mirror image, well, let me do that. Well, anyways, you get the idea. If you take the mirror image and put it right on top of the HOH, it fits on there. So that means that it's achiral. Okay, now the big thing is that chiral molecules are called enantiomers. That is the name of the isomers. There is a left and a right enantiomer. And when you have a chiral molecule, you have what's called a stereogenic center. The stereogenic center is the carbon atom that has 4 different bonds. They have to be completely different. If a carbon atom has only 3 bonds that are different and 2 of them are that are the same, that means that you do not have a stereogenic center. So if you were asked to identify in this molecule where your stereogenic center is, where would it be? Would it be here? No, because those are 2 methyl groups. Those are the same. That's not stereogenic. Is this the same? Are these all things the same? Well, here you have a CH3. I'm just going to write that in. You have this R group. You have this R group, which is not the same as this one. There are different things attached here. And then you have that H. So here you have a stereogenic center. There's one other stereogenic center in this molecule. It's right there. So that's how you can identify stereogenic centers. There is a question on your quiz like this, I think. Oh, no. Not on this coming up quiz. There shouldn't be. Okay. Now, the important thing about this, the reason why we're talking about chirality and chiral, achiral enantiomers is because it has very, very important significance in the medical field. And so I wanted to show you, now when you get your notes, you should be able to go to this link here and it should bring up this article from Wikipedia. I don't normally use Wikipedia, but this is actually pretty accurate here. This article is all about Prilosec and its sister, Nexium. I'm sure you guys, if you were practicing in the early 2000s, you probably remember Nexium and its popularity for treating acid reflux. Nexium is a proton pump inhibitor, which means that it stops your stomach from producing H+ in the stomach, which increases the acid content. We talked about that in acid-base unit. Okay, so I just want to go through this article with you and get through some of the jargon because this is exactly what we're talking about right now. Omeprazole, this is the generic name of Nexium and Prilosec. I'm sure you guys are very familiar with omeprazole. You probably see this a lot. A lot of your patients are probably on omeprazole. Omeprazole is what is called a racemate. Racemate is another word for a racemic mixture, which is a mixture of both enantiomers of a compound. This is like saying that you have a mixture of right and left hands. Omeprazole is a racemate, or a racemic mixture. It contains a tricoordinated sulfonyl sulfur in a pyramidal structure, and therefore can exist in equal amounts of both the R and S enantiomers. Don't worry about all of that other jargon. R and S enantiomers are the R and S is the nomenclature for determining whether it's a left or right hand, is basically all it is. So you have a combination of both the left and right hand enantiomers. In the acidic conditions, blah, 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 blah. So basically it's telling you that they're inhibiting the ability of the parietal cells to produce gastric acid, which is what, the more acid you have in your stomach, the more it's going to bubble up and reflux. Okay, so what happened and why this is all important is that here you have a drug that has both of the enantiomers. And most drugs do have enantiomers. They're very complex molecules. There are stereogenic centers usually in those very complex molecules, which means that there is a likelihood that there is an R and an S enantiomer. A lot of times when you have drugs, only one of the two enantiomers, in other words, one of the two hands, is the one that's effective in the body. The other one is completely ineffective, and sometimes it's even toxic. In the case of Prilosec and Nexium, what happened was, in 2001, the patent for Nexium was going to run out. Nexium is the brand name of the original proton pump inhibitor that was marketed. You probably remember TV commercials in the late 90s and early 2000s for Nexium. So what happened was they were going to run out of the patent for Nexium. You guys know what happens when your patent runs out, right? When the patent runs out, then anybody can start producing generics. When generics are produced, most pharmacies are going to substitute generic for the brand because the generic, in most cases, is significantly cheaper than buying the generic or buying the brand name drug. So what they did was they realized that Prilosec and Nexium are enantiomers of each other. They're the same compound. One is the R enantiomer and the other is the S. And I'm not sure which one is which. I can't remember quite which one is which, but my best guess would be that this is the S and this is the R. I'm not sure on that. So what they did was they discovered that both of these drugs, they're only different in the fact that one's a left hand and one's a right hand of the exact same drug. They were both effective and they both produce the exact same result in the body. So what they did was, when Nexium's patent ran out, they started marketing Prilosec. It's a completely different drug in terms of chemistry. These are two different compounds. All enantiomers are two different compounds because it's they're left and right hand. Just because you have two hands doesn't mean that they're not exactly the same. You use them to do different things. So they have different chemical properties usually, and that means that they can be patented separately as separate drugs. And because they didn't have to do all of the clinical trials on Prilosec that they had already done on Nexium, when they put when they applied for the patent for Prilosec, they got the full 17 years. So that's why you still see a lot of Prilosec out there advertised as the brand name. Because it doesn't, Prilosec itself, I don't think the patent on Prilosec has run out. It is 2012, I'm not sure on that. So that's what they did so that they could still get doctors to prescribe a brand name as opposed to the generic of Nexium, which is also omeprazole. They're just different in that one little place where one of the atoms is going forward and one is going backward. That's not the case in most drugs. In most drugs, only one of the enantiomers is active in the body.